Okay, go live, going live, and we are live. So I'm just gonna let it reflect. And I already see 4 people waiting on the YouTube stream. Yeah,
That's
there you
great.
go. Yep. Okay. So hi everyone. We are just waiting for another couple of minutes for to get a few more people to join and give time for a few more people to join, and then we'll get started. Thank you for joining. Okay, I guess we will get started. Um, the Zoom link is not good, is a message I got in the YouTube channel. So let me put it there one more time, and hopefully that helps. Um, all right. So, hi everyone. Um, Welcome to all who just joined. And we will get started on today's guest speaker talk. Um, this is a club. We are from a club here in San Jose, California. Well, somebody's saying something. Okay, never mind. Um, sorry, we are a club of amateur astronomers here in California, San Jose, and we have been around for many years. And this pandemic really posed a challenge in terms of how to keep going with activities like starry nights, or like star observing parties, star parties, where you are sharing telescopes and whatnot. So while those are suspended, we have kept going this guest speaker program because that was easily movable to an online format. And before you all joined, I was just talking to Carver about how we had to tweak a few things there too. But what has that enabled us to do is reach to the speakers beyond Bay Area, such as himself, who's joining us from Arizona today. So that's pretty brilliant upside of this. I'll take that. But in general, when we don't have a pandemic happening, we are a very active club. We have events going every week pretty much. You can find out more on sja.net, or if you are a meetup person, then you can go through meetup and look for SJ-Astronomy, and you will find our current events there too. With the restrictions opening up a bit, we are talking about how to start doing events in a safe way possible. So if you stay tuned on Meetup, you will be able to see our schedule of upcoming events easily, and you can probably RSVP there as well then to stay in the loop about those events. So with that said, I should have introduced myself actually. My name is Sukhada. I run the guest speaker program. I'm also one of the board of directors of this astronomy club. And today it's my pleasure to introduce Dr. Carver Bierson from Arizona State University. He was actually a California person too until recently, as I understand. He just finished his PhD last year from UC Santa Cruz, and then he's doing a postdoctorate now, fellowship now at the ASU University, Arizona State University. And he has been fascinated with multiple mysteries of the universe, but as I understand, this is his favorite topic, to figure out what are these distant worlds which are frozen and what's going on with them. So without further ado, I'm gonna pass it on to Carver to start speaking on this topic. Thank you.
Thank you very much for that wonderful introduction. Yeah, as you said, currently I'm at Arizona State University, mostly working on NASA's upcoming Psyche mission, which is going to go visit a metal asteroid. But I also spend a lot of my time thinking about icy worlds, and a lot of my past work has been on icy worlds across the solar system, both from previous missions and what to do when we go back to them. And so that's what I want to talk to you all about today. And let me get to my on the right window so I can advance my slides. Excellent. This is one of my favorite graphics. I consider myself a planetary scientist, but I spend most of my time thinking about the not planets of our solar system. This array of beautiful and diverse worlds of all different sizes and compositions, different distances from the sun. This lovely graphic, which I'm going to keep coming back to throughout the course of this talk, is put together by Planetary Society. And this includes a lot of moons, mostly of the outer giant planets. So at the top, we have Jupiter's 4 large satellites. We have the Earth's moon here, the largest satellites of Saturn, Uranus, Neptune, and then Pluto and its largest satellite, Charon, and some asteroids as well. So a smattering of objects from many different places across the solar system. And most of these worlds, I'm getting a little bit of echo from somebody on the channel. Most of these worlds are icy worlds. Most of them have a lot of their mass as essentially water ice, with a few exceptions, like our own moon is very dry. But despite the fact that these are largely icy worlds, there's only 3 of these that I think most people within the community would all agree have oceans on them. And those 3 are Europa at the top here, Saturn's largest moon, Titan, and one of the smaller moons around Saturn, Enceladus. These are the 3 that I think if you talk to almost any planetary scientist, they would agree, yes, these 3 have oceans. And I'll come back to many of the others later on, because if we're talking about which worlds definitely don't have oceans, there's only a handful of those as well. Certainly our moon, Earth's moon, doesn't have a subsurface ocean because, as I said, it's dry, it's made of rock. Jupiter's inner moon Io, which is this brightly colored yellow moon, also it's just made of rock. There's not enough water there to have an ocean. So those are easy to rule out. Some of the asteroids get ruled out for the same reason. And then there's a few worlds that are very small and have no heat sources, which I'll talk about later, that could reasonably support an ocean. So most of the worlds on this image are in neither category. They don't definitely have an ocean, but they don't definitely not have an ocean either. So over the course of this talk, what I want to do is give you a sense of how we find these oceans, how we think these oceans come to be, how they're formed, how they disappear with time, and how we might detect them on some of these other worlds, or ways we might have detected them already. So to start with, let's go through the three that definitely have oceans. And in some ways, this is a nice case study, because on each of these, we found the ocean using a different technique. The first icy moon we found an ocean on was Europa. This is a Galileo image of Europa. And even just when you look at the surface geology of Europa, it's very smooth. Well, I say smooth, it's not cratered, but it has huge cracks running along its surface. It just feels like a world where things are shifting and moving on the surface all of the time. There have been many people who try to kind of move the cracks back in time in very similar ways that here on the Earth, we try to reconstruct plate motions back in time by seeing where different things would have fit together. And that certainly hints that this top thin layer is mobile, it's moving around. The easiest way to have that happen is if it's floating on an ocean beneath. And so that surface geology is hinting at the ocean, but the real discovery, the real thing that clinched it, wasn't the surface geology. But first, let me talk a little bit about the spacecraft that did this. Galileo mission was set to launch in the late 80s, and it was set to launch on the shuttle, on the space shuttle. But when it went, it was shipped down to Florida, to Kennedy Space Flight Center, to be loaded up on one of the next shuttle runs. And then the Challenger disaster happened, and all the shuttles were grounded for almost 5 years. And so what happened is the Galileo spacecraft during that time didn't have a ride to space. It sat in a warehouse in the Florida heat for almost 5 years, just waiting, fully built, fully assembled, ready to go. Once the shuttle program got going, it was able to be launched and went out to space. The engineers sent the command to have it open up its main radio dish, which had this unique design where it started folded so that it could fit into the shuttle bay, and then it was going to open up. And when they sent that command, it couldn't do it. They tried several more times, and the main dish wouldn't open. That's why in this kind of computer render, they have the main dish kind of locked up. The thinking is that probably something happened. Maybe something happened with the oils that lubricated these joints during those 5 years of Florida heat and humidity that it was stored in that caused some malfunction. We don't really know what it was. But that meant that the duration of the mission, it could only send back data on a separate low gain antenna, which wasn't meant to be used for sending data from Jupiter back to the Earth. And so it sent back far, far less data than it collected, far, far less data than it was intended to send back. And even with that, it sent back the best images we have, largely of all of the large moons of Jupiter. And it's the mission that confirmed this water ocean under Europa's surface. The way it did this was measuring the magnetic field, essentially Jupiter's magnetic field, as it passed close to Europa. And unfortunately, this sort of detection doesn't lead to pretty pictures. It leads to somewhat ugly plots like this, which I'm not really going to explain, but essentially you're measuring the magnetic field as you're passing by the satellite. And they notice these deviations from a straight line, from what's happening in the surrounding area. And the reason for these deviations is because of magnetic induction in Europa's ocean. Induction is the physics we use to generate essentially all of our electricity, or nearly all of it, in society, regardless of the method. Induction is just that when you have a magnet or a magnetic field that's moving or changing with time near something that's conductive, say a wire, it causes electricity to flow within that wire, within that conductive medium. So here on the Earth, when you spin a wind turbine, there's magnets on that wind turbine, and you have a coil of wire next to that. So the coil of wire sees this magnetic field that's changing with time, and that generates electricity. Coal-fired power just uses the steam that it heats up with the coal to spin a turbine that has magnets on it for essentially the same method. But the key is that when you move that electricity within that wire, you move those currents, they create their own magnetic field, and that can be detected by a spacecraft flying by. And it just so happens that Europa is sitting in the biggest magnetic field in the solar system, if you don't count the sun. And Jupiter's magnetic field is tilted so that the north pole of its magnetic field is not quite at the north pole of Jupiter, similar to what we have at the Earth. So as Jupiter spins, every 10 hours is a day on Jupiter, that magnetic field comes sweeping past Europa. It changes with time, and it causes currents to flow in Europa's ocean, probably because of salts in that ocean or something else that can carry an electric charge. And that could be detected by the Galileo spacecraft as it made several passes close to Europa. So a little bit of an indirect technique, but it gives us this really the first of its kind of discovery, that under the surface ice, there's an ocean. This technique, unfortunately, doesn't tell us how thick the ocean is, or conversely, how thick the ice above it is. It tells us that the ocean must be at least somewhat salty, but we don't know exactly how salty. And so these are questions that we need to return to Europa to answer. Now, something to address is that there's recently been talk of other methods to understand Europa's ocean. Been talk of plumes at Europa. And this was first announced by work by Roth et al. In 2014. And the bottom two panels here are Hubble images of Europa in very particular wavelengths of light. And what they argued in this initial discovery paper is that this little blob in the lower right-hand image in this very particular wavelength indicates a eruption or a plume of material coming out of the surface. And in the years following this announcement, lots of groups have looked at Europa in the same wavelength of light, and it's been a mixed bag. Mostly we don't see anything, which doesn't mean that this is wrong. It could just mean that it's a rare event. We don't really know how common this should be on a world like Europa, where people think they might see something. It looks like it's happening in maybe different places from this initial detection, which again doesn't tell us that it's not happening. But we certainly haven't had enough evidence to say that this is definitely correct, because these images have noise. And if you take a lot of these, as many groups have done now trying to replicate this, you're going to see a few that are noisier than others. Some of that noise is going to be at the limb. So for now, we don't know if there's plumes at Europa. There's this hints of it, this kind of very provocative evidence that it might be there, but nothing surefire. And so this is why the Europa Clipper spacecraft is currently being put together. They're in the last stages, I think, of essentially the design, finalizing everything, getting all the pieces ready to be assembled. And Europa Clipper is set to arrive at Europa around 2030, depending on the details of the launch. Europa Clipper has instruments like radar, which is for the first time going to tell us how thick is Europa's ice shell, how thick is the ocean under that ice shell, and hopefully give us some composition information as well. Start to learn more about what's the red material on the surface. It amazes me that on a world like Europa, we still don't really understand why are the cracks red? What makes them that way? We think it's probably some sort of salt, but saying probably some sort of salt is not the most satisfying answer. There's a lot more to be learned. All right, so that's how we know there's an ocean at Europa, but why is there an ocean at Europa? This is a world where the surface temperatures are 100 Kelvin, which is freezing. It's like minus 300 degrees Fahrenheit, almost that. This is a very cold place to be in the outer solar system. In the future, I'm going to be talking about other even colder places in the solar system. So how do you keep a subsurface ocean? On Europa, it's tidal heating. This is an image from the Voyager spacecraft as it flew past. You have Europa down in the kind of lower left here, and its shadow on the surface of Jupiter. In this image, you also have the Great Red Spot there, which is about 3 times the size of the Earth. Because Europa is so close to such a giant planet, the mass of Jupiter is distorting the shape of Europa. And Europa's orbit is not perfectly circular. So the way tidal heating works is something like this. These are essentially a top-down view. And on the left, I have the way we typically think about orbits. So you have this elliptical orbit, highly exaggerated, of Europa around Jupiter. And because it's elliptical, it gets closer and farther away. And on the right, I have a view where I'm just going to hold Europa stationary. And from the perspective of Europa, Jupiter kind of goes back and forth in the sky a little bit because this elliptical orbit, and it comes a little bit closer and it gets a little bit farther away. So as Europa goes around its orbit, it's both rotating and it's accelerating towards Jupiter. And as it does this, as it gets closer, there's this bulge that's going to form. Jupiter's pulling out bits of Europa closer to it, these tides. But because Europa's speeding up, that tide doesn't look exactly at Jupiter. It actually kind of misses and gets pulled away a little bit. And as Europa gets closer, that tidal bulge is going to grow and get larger and then shrink as Europa gets farther away. And it's this stretching and squeezing of an entire satellite as it gets closer and farther away that causes a lot of friction. You have big sheets of ice that are going to be grinding against each other, and that dissipates heat in the interior of the satellite. Closer to Jupiter from Europa is its neighbor Io, which is maybe the best example of tidal heating anywhere in the solar system. Io doesn't have an ocean because it has essentially no water on it at all. So instead, all of that heating that it gets from the tides from Jupiter goes into forming volcanoes. Io has something like 400 active volcanoes at the surface. When we point Hubble or other telescopes at Io, there's always volcanoes erupting. It's just a question of which ones on that particular day. It's a remarkable world in its own right, and could be the focus of a whole nother talk here. But for now, keeping on ocean worlds, let's move a little bit farther out in the solar system to Cassini. Galileo was visiting the Jupiter system through much of the 90s. Cassini arrived at Saturn kind of as that mission was winding down. It arrived in late 90s through the 2000s, essentially. And one of the first discoveries that Cassini made in the Saturn system was it took pictures of Enceladus, a small moon that wasn't thought much of, other than it had a little bit of weird surface geology, but lots of moons have weird surface geology. But you take pictures of Enceladus and it's almost inevitable that you see water shooting out of its surface. This is maybe the most obvious way to detect plume or an ocean on any world. It's just the water is there, spraying into space. There's so much that it has created its own ring around Saturn. It's called the E ring. That is material erupted from Enceladus over the past however long it's been doing this. And because of these plumes, it's one of the most photogenic worlds in the solar system. There's a few hundred plume sources or geysers on Enceladus, but all of them are concentrated in the southern hemisphere, right around the southern pole. This is a thermal image of Enceladus taken by Cassini, and most of it seems unremarkable, kind of the surface temperatures you'd expect, except right near the southern pole. There's these four, what we call the tiger stripes, these four large fissures near the pole. And all of the geysers are concentrated around these. And we don't know why. That is very much an active area of research. Tidal processes in general, we expect to act the same north and south. So if there's a lot of tidal heating dissipated in the southern hemisphere, we expect a lot in the northern hemisphere as well. But that's not what's happening. All the geysers are in the south. And so this is an area where we're still very actively trying to understand what's going on. Why is it the south? Was there a giant impact that kind of kicked things off and warmed up the ice so that it dissipated energy better here than other places? Or did something else happen? We don't know. But Enceladus is a good reminder too that tidal heating can be temporary. Right now, evidence seems to show that Enceladus does have a global ocean in its interior. So this cartoon is a little bit wrong. The liquid water probably wraps all the way around the core, all the way to the northern hemisphere, but it's thicker in the south than it is in the north. Again, for reasons that we don't fully understand. But when we have these eccentric orbits that are causing this tidal heating, that eccentricity can change with time. And tidal heating in general will try to essentially steal some energy there. As you're dissipating this energy, your orbit is going to get more and more circular until your tidal heating shuts off or something else kicks your eccentricity up again. For Europa, it's in as close resonance with the inner moon Io and the outer moon Ganymede, and these three moons all interact in a way constantly bumping up each other's eccentricity. So Europa has probably been feeling this tidal heating for the entire history of the solar system. Enceladus, we think, may be a case where this has turned on more recently, and it hasn't been the entire history of the solar system, but we don't know how long it's been or exactly how much longer it will last. The other moon in the Saturn system that we are very confident has an ocean is Titan. Titan's a moon, but it is a big moon. This is the second largest moon in the entire solar system. It's bigger than the planet Mercury. This is a big world. It has an atmosphere that is thicker than the Earth's, although the gravity is less because it is still much smaller than the Earth. It's very much an icy world. It's very cold surface. There's no plumes coming out. In fact, we can barely see the surface. Anytime you look in visible imagery, it's always going to look like this. You see hazes in the entire atmosphere. So in order to detect an ocean, we had to do something different. Unfortunately, magnetic induction, like we used at Europa, doesn't work in the Saturn system at all. Saturn's magnetic field, it turns out, is perfectly aligned with the spin pole. And so from the perspective of the moons, it never changes with time. And if you have a magnetic field that doesn't change with time, you get no induction whatsoever. So what do we do at Titan? Well, for Titan, we can measure its gravity. Cassini did several very close flybys of Titan, where it pointed its radar dish essentially at the Earth, so that from the Earth, we could very carefully track exactly where the spacecraft was as it flew past, and detect very small changes in Titan's gravity. And this gives you a very good idea of Titan's shape and how Titan is being deformed by Saturn itself. And we can use this because if Titan was totally frozen, like on the left here, then you have a solid frozen ice shell on top of a, say, rocky core. And that is all very strong. And that's going to hold its shape really well, even as Saturn pulls on it. But if there's a liquid ocean under a floating ice shell, well, now that ice shell is decoupled from the core, it's just floating there. So it can stretch and squeeze separately from the core underneath it. The core can't support it at all. And it's more like this scenario on the right that we saw. We saw a Titan that's far more consistent with it having an ocean underneath. And in fact, gravity is one of the best tools that we have for understanding these subsurface oceans. That's how we know Enceladus's ocean goes all the way around the core. And Europa Clipper is going to be working really hard to get a lot of good gravity data for Europa to determine that ocean thickness as well. Titan is, this point. Titan's internal structure is much more complicated though. Because this is such a huge moon, it's got crazy things going on. It has the surface ice shell, which is ice like we think of it. And then it's got liquid water ocean. And then under that, there's actually more water ice. There's this higher pressure phase of water ice called ice 6 that can only exist in very high pressure situations. And then a rocky core underneath that. And it has this, again, complicated, big, deep structure because this is such a huge world and one of the largest icy worlds in the solar system. And Titan's surface is one of the most dynamic of really any moon in the solar system as well. I mean, this is an image from the Huygens descent probe, which was attached to Cassini, or basically rode along with Cassini to Saturn, and then fell through the atmosphere of Titan. And this was an image it took on its way down. And you can see river networks feeding into a lake. Titan has lakes at its North Pole that are filled with these liquid hydrocarbons, things like propane and ethane. And Titan looks like a world shaped by a liquid flowing across its surface. And so this is one of the reasons why NASA selected the Dragonfly mission, which is currently being built and will arrive at Titan around 2036. And this is a octocopter. It has 8 rotors on it. It's going to fly around Titan's, mostly the equatorial regions, where there's a lot of these giant dunes. And I want to call them sand dunes, but we don't know what the sand is made out of. We don't know if it's ice that makes up these dunes or if it's some sort of organic carbon gunk. We just don't know. So Dragonfly is going to go, it's going to sample that material that makes up the dunes. It's going to move around to different locations because it's a very mobile platform. And that's going to be an incredibly exciting mission. So the 2030s are going to be a great decade for understanding these icy worlds in the outer solar system. In terms of powering Titan's ocean, though, it's not tidal heating. Titan is really far away from Saturn, so the tides just actually aren't very strong in terms of delivering energy. And it's also got a much more circular orbit, so it doesn't actually dissipate very much energy. So how does it keep an ocean then? Well, it uses its size, essentially, and radioactive heating. Part of what keeps the Earth's interior warm as well. Radioactive heating works much better on bigger worlds because you have more rock in your interior, and the rock is what's going to have most of those radioactive elements. It's going to be mostly things like uranium, thorium, and potassium that deliver their heat over solar system timescales, over billions of years, so that you can keep an ocean around for billions of years. On small worlds, that radioactive material is too close to the surface. So as you produce that heat, it just immediately gets leaked out to space. But on a big world like Titan, you have this really thick ice shell that essentially can act like a blanket. It can insulate the interior, keep the interior warm, even as you have very cold surface. And when you have radioactive decay heating your ocean, you're going to generally end up with a history, we think, that looks something like this, where Titan probably formed very cold. Over time, the radioactive decay releases more and more heat into the interior that can start to melt that subsurface ocean. But then at some point you start to run out of these radioactive elements. And so that ocean's going to begin refreezing. Now, Titan's ocean hasn't totally refrozen. It still has some ocean left. But there's probably other worlds a bit smaller than Titan that used to have an ocean, but now don't, where it's totally frozen solid. So that's our 3 definitely has an ocean worlds. Let's get into some more speculative ones. And for that, let's go a little bit farther out in the solar system. A New Horizons spacecraft was launched in 2006. At the time of launch, it was the fastest spacecraft ever launched, going something like 3 times faster than a bullet or something absurd like that. It gets out to the Jupiter system in 1 year, a journey that takes many spacecraft 5 years. Most of our spacecraft take a year to get to Mars. And still, it took 9 years for New Horizons to get to Pluto. By the time it got there, it had so much speed that there was no chance of slowing down, and it didn't intend to. It took a series of images as it flew past Pluto and is continuing out through the Kuiper Belt. Just 2 years ago now, we flew past another smaller Kuiper Belt object called Eris, and the team is actively looking for more Kuiper Belt objects to image before the spacecraft leaves the Kuiper Belt. When we got back the images of Pluto, Pluto turned out to be a more dynamic and interesting world than I think anyone expected. It's a world with an atmosphere that has hazes. The surface is covered with lots of different ices, which are being exaggerated in color to show the different materials that coat the surface. There's carbon materials that have been processed, some sort of organic gunk there as well. This big basin right in the center of the image filled with nitrogen ice. And big cracks running along the side. This image of Pluto is essentially a zoom in of the one before, but it's been recolored to about what Pluto probably looks like. It's the closest to true color we can get with the cameras that were on New Horizons. And for this crack that I'm pointing out in particular, we found evidence of fresh water ice exposure and fresh ammonia. And that ammonia is important for 2 reasons. First off, ammonia doesn't last that long on the surface of Pluto. It gets destroyed over time by high energy particles coming from the sun and from the galaxy. And ammonia is also a very good antifreeze. So if you have a large ocean that's slowly refreezing over time, that ammonia is going to get concentrated in the water more and more, trying to keep it liquid as everything cools off, until your last bit of ocean is going to be enhanced significantly in ammonia, depending on how much you started with. So this appears to maybe be some little bit of that ocean that's been able to find a way to the surface to get out in the relatively recent past. We don't really have exact ages for anything on Pluto, so I'm going to use a lot of vague terms like relatively recent or ancient, and lots of hand waving involved in those ages. Pluto is big enough that radioactive heating could have formed an ocean. And there's different opinions in the community about whether it can keep that ocean all the way to the present day. But things like this seem to hint that maybe it did. Maybe the ocean did survive and is still there under the surface on Pluto today. That doesn't actually tell you when it got there, because there's one more energy source you can use to build an ocean, and that is the heat of formation itself. Building worlds is not a gentle process. You have a lot of material, a lot of mass that's coming in at high speeds, colliding with each other. And as it collides, it has a lot of energy to get rid of, so it heats everything up. And you can heat up that surface more and more. Now, if you form a moon slowly, you have one impact come in, warm up that surface, and you have time for it to cool off to space before the next one comes in, and then you can cool off that region. But if you form really fast, you don't have time to cool off in between impacts, and the surface just gets warmer and warmer and warmer. And so you get a scenario that's more like this, where maybe some of these worlds formed with oceans really early on, and those oceans have just been cooling steadily over all of solar system history. Again, maybe they've totally refrozen, or maybe there's still a little bit left. Radioactive heating helps keep that around for a bit longer. If there was no radioactive heating, there's no way Pluto would have an ocean, even if it started with one. But starting with an ocean can help a little bit. And there's ways that we could actually look for evidence of this early ocean. If you take a water bottle and stick it in your freezer and leave it there, that water expands as it freezes to ice. Ice takes up more volume than liquid water. Same thing happens on icy worlds. So if on the left is the opposite example of this, if we're taking an ice shell and we're melting it, then we're going to be compressing it. It wants to take up less volume. And when you compress a world like this, you're going to build mountains. The classic example on the Earth would be like the Himalayas, right? You have two plates colliding together. That's compression. You're compressing them together, and so you build a large mountain range. If we on the right, we have that example of freezing. If you freeze an ocean, you're going to expand. Your surface needs to get bigger. You're pulling it apart. You're going to form large cracks. And so if Pluto started as this solid ice shell that melted, we should see evidence of early compression, early mountain building, and then later on, maybe some extension as it starts to freeze. But if Pluto started with an ocean, it should have just been freezing essentially for all of solar system history. So Pluto has been slowly growing and pulling apart and forming more and more of these wide cracks. So what do we see at the surface? Well, we see lots of these cracks that I'm pointing out in the same image here. All of these appear to be extensional, where the surface is being pulled apart. And when we look at the oldest trains of Pluto that we think are at least close to the age of the solar system, probably very old, we don't see any evidence of compression. We don't see any evidence of large-scale compressional features like mountain ridges and things like this. And some of the oldest topography that we see, this is a topographic map of Pluto. Some of the oldest topography you see is some of these like very straight lines in here. Again, seems to indicate extension, telling the story that maybe Pluto started with an ocean, and it's been slowly refreezing for all of solar system history, because maybe Pluto formed very fast, which would be consistent with work of other groups that model how quickly the worlds like Pluto in the outer solar system formed. This kind of fast formation and early oceans may also apply to Jupiter's satellites, particularly Europa, which probably formed in a relatively warm region, much, much closer to the sun than Pluto. And also Jupiter was there close by, which also made this a really warm region. So Europa may have also had very early ocean that's been maybe not totally refreezing because you have that tidal heating to keep things going, but at least changing throughout all of solar system history. And then you also have Pluto's neighbors. This is the best images we have from Hubble Space Telescope of Eris on the left and Maki on the right. These are worlds similar in size to Pluto in a similar part of the solar system. And we think they formed in similar ways. So there's good reason to think they could also have subsurface oceans. But for now, when these are the best images we have, we just don't know. And we need spacecraft to go exploring to see what these worlds are truly like and what their surfaces hold. Even a little bit closer to us, there's the moons of Uranus. These were visited briefly by Voyager 2. And I think that flyby revealed more mysteries than anything else. This is just the inner moon, Miranda, and its surface is filled with these kind of straight lines and some swooping features, some craters, and I don't think anyone in the planetary science community really has a good handle of what's going on here. This is an incredibly strange surface. It's sometimes described as chaos terrain, for lack of a better term. But certainly this moon has experienced something dramatic in its past, probably a lot of tidal heating. Did it have an ocean? Does it have an ocean? We don't know. We'd have to go back, and there's a lot of active discussion right now about how we might want to build a spacecraft to go visit the moons of Uranus. There's also Neptune's large moon, Triton, which again is about the same size as Pluto. We think it probably has a similar composition of Pluto. Probably formed in a similar way to Pluto, and then it got captured by Neptune and became its largest moon, probably throwing out most of the other moons that were there in the process. And currently there's a mission under review by NASA, which may be selected to fly, that would fly past Triton and try to address this question: is there a subsurface ocean there or not? So as I kind of wrap things up here, I'll come back to that starting graphic. There are 3 worlds that I've circled that definitely have oceans. We have a handful that I've crossed off as definitely not having an ocean. And there's many, many more. The ones that I've put question marks here are ones that at least somebody has said, yeah, this world might have an ocean, that there's some evidence for it having an ocean either recently or at the present day. And we just need more information. We need to return to these worlds to really understand if those oceans are currently there or not, and what their histories are. So I'll leave you with this and take your questions. Thank you very much.
Thank you so much, Carver. That was wonderful. Let's see, we can all, I think we have a few people in the Zoom session, and if you have questions, feel free to unmute yourself and ask the question. If you prefer I relay the question, then type it in the chat and I will do so. And also I'm just checking the YouTube chat channel if anybody has posted any questions there. No questions on YouTube. But it's a little behind, so maybe we'll catch up there in a bit again. Any questions from the Zoom audience? Wow, quite cute crew today.
Give my voice a chance to recover here too.
Yeah, sure. Take your time. Completely understandable.
What are the plans, if any, for a spacecraft that would penetrate ice and go below the surface into these submerged oceans?
Yeah, so there's a lot of active discussion right now, particularly focused on Europa. And there are groups that are thinking about if you went to Europa, how would you get through the ice? How would you go and explore this ocean? And these are at a fairly early stage of development right now, so there's not like clear concept that everyone is behind. There's a lot of questions, in part because there's still a lot of open questions about Europa. If that ice shell is only a few tens of kilometers thick, that's a lot easier to get through than if it's 100 kilometers thick. And so the fact that there's still so many unknowns makes it very hard to plan a mission that would go through the ice to access the ocean. On a world like Enceladus, it's actually a lot easier because the ocean comes to you through these plumes. So the Cassini spacecraft actually got to fly through the plumes, and it had a mass spectrometer on board, so it could do some basic chemistry and found a variety of salts in that water that were very concentrated. But when we're talking about understanding the chemistry, we would also love to know, like, are there organics? Like, you know, is there anything down there in those oceans? Unfortunately, as Cassini flies through, it's flying through at kilometers per second. And organic molecules are very delicate. So if they were there, they probably got destroyed when they impacted the detector. So it's hard to like recreate those fragments and say, well, what did they used to be before they went into the instrument? But maybe future designs planning for that. Cassini didn't know that there was plumes to be flying through when the spacecraft was built. Maybe future designs we could do something to try and mitigate that, to sample that ocean and really understand what's in there.
Thank you.
So Marianne has a question. Can you address the possible chemical makeups of some of the oceans?
Yeah, all of the oceans are going to be predominantly liquid water, but with a variety of different salts and dissolved gases in them. And some of those salts are going to be things like the salts here we have on the Earth, like magnesium and sodium chlorides. We also think that there's probably a fair amount of ammonia because we see a lot of ammonia in the atmospheres of the outer planets and in comets. Comets are kind of our best proxy for the different ices we think might be out there because they're a little bit of the outer solar system that comes in to visit us to make it easier for us to sample. But in detail, we don't know the compositions of these oceans because we haven't been able to sample them. We don't know how much these oceans are able to pull up different chemical ingredients from their rocky cores underneath. You know, how much hydrogen and sulfur species are you able to grab up? Because those are the things that we think might be food for any microbes that could possibly survive in these oceans. And we just don't know how much is being produced, how much is finding its way into the ocean.
Okay, that's pretty cool. One question that has come in on the chat channel, actually a couple of them. So one question is, I'm assuming this is for you. Have you ever been to space?
No, I have not. I'm not much of an adrenaline junkie, so I'm not sure I would want to.
You don't want to go to one of these icy worlds yourself?
No, I'm happy to send our spacecraft ambassadors and look at the beautiful images
Actually,
that they send back.
The 2036, is it? The mission you showed, that looked pretty cool. I mean, that looked next level from what we just sent to Mars, for sure.
Yeah, Mars feels like a mini test run of this. And in fact, Dragonfly going to Titan. Titan is like the perfect place to fly a robotic copter because there's more atmosphere than the Earth. So you get more lift from each of your rotors and there's less gravity. So you don't need as much lift. And so it's just perfect. We think from Cassini that the winds are fairly calm at the surface, but to be honest, that data is not the best. So we're kind of hoping, and we think that this design could handle it even if there are more winds than we might expect.
I see. Actually, that is a perfect segue into the next question, which is what inspired the design of Dragonfly?
Ooh, that's a question that I am not going to be able to answer because I'm not directly on the Dragonfly team, and I haven't asked the people who are running the mission that question. So yeah, I don't know, but it is a very cool mission concept, and I think one of the most exciting that we have
yeah.
coming up.
I can see that. It looks pretty cool. And we managed to fly a helicopter on Mars. So I guess this is going to be the next one.
Yeah, this should be much easier, I think, too. And it's been working great on Mars. So it's excellent.
Yeah, that mission's Perseverance was a huge success. Sorry.
Yeah.
Let's see. I don't see any more questions in the YouTube chat channel.
I have a question.
Oh, go ahead.
Can I go ahead? Hi, I'm Marie. I'm just curious. It takes so long for anything coming from Earth to get out into outer space, whether it's to the space station or to explore all of these planets. Is there, I mean, I'm sure NASA is trying to find ways, but are you aware of anything specifically that's being done to kind of speed up the whole journey?
Yeah, it's so difficult. In some ways, to get to the outer solar system faster is easy. You just need to go faster, which just means you need to burn more fuel. The problem is that that's really expensive. And so it's a trade-off between the time it's going to take you to get there and the amount of money you want to spend to get there faster. And there are some periods of time that are just cheaper because you can fly by several planets. They can give you an extra kind of speed boost for free without needing to burn extra fuel. This is why New Horizons flew past Jupiter, was to get an extra speed boost as it flew past. So this is a process that NASA is always thinking about, always working on. In fact, these missions are timed very specifically to take advantage of the planets being in the right location to get these flybys, to get extra speed. But at the end of the day, it's just really far. And especially if you want to slow down enough to get into orbit or to land, slowing down also costs fuel. So the faster you're going to get there, the more fuel you need to bring to slow down once you arrive. And that's why New Horizons didn't go into orbit, because they wanted to get there fast. And fast in that case was 9 years. And that means there's no way they could have stopped to get into orbit. If they were going slow enough to get into orbit, the mission probably would have taken 10 years longer to arrive. So
Tricky business.
Trade-offs. Yeah, it is. It's all about these trade-offs.
Thanks for explaining that. I appreciate it.
Let's see. No more questions in the chat channel here. I'm gonna check the YouTube one more time. No questions here either. Oh well. So actually, I have a question. So speaking of Dragonfly, it's in your current work, are you collaborating with NASA on this? Like, how does this work when there are researchers actively doing research in this field across the country, potentially around the world, when NASA is planning a mission which is specific to that area? So could you talk a little bit about that?
Sure. So the way that NASA's mission programs in general work, this was true of Dragonfly, is that lots of different groups of scientists and engineers from different institutions come together and create teams around an idea for a spacecraft. And some of those will get put together and they'll get submitted to NASA, and NASA will pick a selection of those to work on further and really refine the design and tighten all the nuts, figure out exactly how much is it going to cost, how long is it going to take, what's all the resources you need. and then it will pick maybe 1 or 2 of those. So right now we're in one of these periods of time. There's 5 missions kind of on the table that NASA's going to choose from. And sometime in June, don't know exactly the date, but probably sometime in the next month or so, NASA's going to select one of these missions, which might be the mission to go visit Triton. It could be a mission to go visit Venus, or it could be a mission to go visit Jupiter's moon Io. These are all kind of on the table. And once one of those missions gets selected, that team gets funded to build the spacecraft and fly it. And once the spacecraft is there, they might bring more scientists on to help them analyze their data. But one of the best parts about NASA is that once that data comes back to Earth, it gets shared publicly with the world. This data is paid for by US taxpayers, and NASA thinks it belongs to those taxpayers. So for New Horizons, which is the mission I've been involved with most closely, we were getting data back from Ericos, those images. We were getting the raw versions up, or at least some version up on the web within 24, 48 hours, essentially as fast as we could. We're getting the data down, trying to turn it into images, and then get it out to share it with the world. And then it's free for all researchers to access, and the whole planetary community can come around and use this data to understand these worlds the best we can.
That's pretty cool. Well, looking forward to it. 2036 is not that far, right?
Yep.
Just 15 more years. It'll fly by.
And we'll have Europa Clipper in around 2030 as well. And the Europeans are also launching a mission to Jupiter's satellites that's also going to be in the 2030s called JUICE. So a lot of missions in the outer solar system around the same time.
Expanding our horizons is what it's all about. So yep. Certainly. Well, thank you so much for your time today and coming to, virtually coming to speak to us. We would love to host you in person sometime if you ever visit California, and if we have an opportunity to go back in person, first of all. Well, actually, there's one last question. Let me just quickly ask that. Sure. How rare is water in space?
Water is very common, actually. In terms of what makes things more common, essentially the heavier an element is, the more rare it is. So hydrogen is the lightest element. It is the most common element in the entire universe. Mm-hmm. And oxygen isn't that heavy, so it's also pretty common. In terms of worlds in the solar system, a lot of the worlds that I'm showing on a graphic like this, something like 30% of their entire mass is water. Close to that. Some of them, it's more like half of their mass is water, and only half of it is rock. The Earth is actually pretty dry, and that's because it was formed in the hot part of the solar system, where it was just too warm for water to freeze out and then get accreted. But things that formed in the outer reaches of the solar system, where things were much colder, you had a lot of water ice. Very common.
Interesting. Well, it's funny you mentioned that Earth is fairly dry. I mean, we have like what, 79% is water, 75 to 79, something like that.
It's just a thin skin right on the top.
When you put it in the context of the whole universe, I see what you mean. So, all right. I guess would be our last question.
Can I ask a last quick question?
Sure, go ahead, Mari.
You talked about the data being shared rapidly, that's collected from the various spacecraft. Have you ever had surprises where some young junior astronomers in elementary school or high school make an observation, have come up with something that the more experienced people have not, just because of their curiosity and untrained eye?
I'm not sure if I have an example of this right off the top of my head. What I would say is that a lot of these missions, including New Horizons, have instruments on board that are led by students, that are built by students from one or several universities. And those students get to be like in the room as the data is coming down and in those conversations, and their opinions are very welcomed. As the data is coming in, it's new stuff, so it's surprising to everyone. And yeah, the more voices you have just saying what you're seeing can be really helpful. Yeah, I can't think of an example off the top of my head of somebody like bring up a new observation, but that certainly doesn't mean it hasn't happened. I just don't know about it.
Thanks. It's okay. It was just one of those thoughts that popped into my head.
Yeah, certainly I will say that amateurs actually help in image processing a ton. Actually, the best example of this is JunoCam on the Juno spacecraft, which is currently in orbit around Jupiter. And those images are sent straight back, and it's almost all citizen scientists who process those images and turn them into just absolutely gorgeous, essentially works of art. I've had one of those Juno images like printed out and hanging on my wall in the other room because they're absolutely gorgeous. And Juno doesn't have a science team that does that. That's all done by volunteers.
That's pretty cool. Another advantage of sharing the data, of course.
Yeah.
Yep. Okay, I think, let me do one last minute check. Okay, I think that's it. That's a wrap. Well, thank you everyone for joining today, and thank you, Carver, once again. I'm glad you all enjoyed the talk, and stay tuned for the next one. We'll post events on the meetup as always. Thank you. Good night, everyone. I'm just gonna end the stream.